Hello and welcome back to the lab. Today on the bench we are staring at the trigger board of a 475A. This is starting to become a familiar sight in the lab, and we're going to be talking about the transistors that I have been replacing in a couple of the 475A videos that I've done in the past. Recently I've been in some discussion with some of the people over on the TekScopes forum or mailing list, and we've been talking about the issue with the 151, I think they're 0637 transistors. If I'm dyslexic on that, let me know. But I'd also like you guys to weigh in on the comments as to what you think. So I've done some additional testing on the transistors. Other people have done some additional testing on the transistors. We're going to use some of my test equipment here in the lab that's available to us, and I'm going to show you some of the testing that's been done on the transistors. And we're going to use some of the more exotic gear to test some of this stuff as well. As noted in the previous video, which I'll link in the description below, questions came up that it made sense to make an additional video on this topic. So in this video, as of yet, there has not been a conclusion. Spoiler alert. But I would like to know all of your guys' thoughts in the comments below as to what's going on. I'm going to show you what's going on. We're going to talk about what's going on and look at some evidence. As most engineering problems, it ends up being clear as mud. So here we go. We're going to pick a random transistor here to pick on. We're going to go with this one right here. So, in that original video, these transistors are 1510637-00 is the part number. And if we take my peak transistor tester and we run a test, we will see the part checks as we would expect for this fault problem to show up as a NPN silicon BJT, which it is. But then we have this diode that shows up here. And this is the real question, is this transistor faulty, or is this behavior that's developed over time, or was this way from the factory? A lot of the transistors in this chain are selected and graded by Tek on their incoming. This one doesn't have any of the colored markings in it or anything like that. But one of the things that I do where I think we're at is I think the device was misidentified. And that's because of a document that's available on the TekScopes forum. So we're going to pick on this same transistor throughout this entire video. That's where it comes from. This is the trigger path of the scope. On the trigger board itself, if you did want to do a transistor replacement for all of these transistors in this unit, it would be 15 in total. I think there's 13 on this board, and then there's 2 more on the bottom. There's one in the horizontal sweep section, and there's one in the power supply for the Z-axis amplifier is where these are in circuit. And these were used extensively in the trigger circuit in the 475. The interesting thing to note here is they were not used in the 465, and they were not used in the 485, and they were not used in some of the faster 7000 series plugins. Okay, first place to start. We need to start on the computer a little bit because we have some documents we have to look at. Right here is the TekXref free PDF. This can be acquired from the TekWiki. This is the cross-reference to Tek part numbers to what transistors actually are. So we'll pop this open real fast. Now, this one has been OCR'd, so we can search through it real fast. So what we'll do is we will search for 151-0637-00. Part of the initial confusion is right here on page 914, or 176 of the document. We have this tech part number, 151-0637-00, and this cross-references to an MPSH05. And this is a 600, if I'm reading this column right, I believe it's a 600 megahertz transistor. Yes, it is a 600 megahertz transistor, and we have a collector emitter breakdown of 80 volts. So this matches the datasheet of the MPSH05 and is all right. Well, if we keep searching the document, we hit the MPSH05 again. And again. And again. And that's the end of this document. There's another document. Let me go pull that up. So here we have another PDF, the semiconductor cross-reference document. So let's take a look at this one. Okay, I don't know why my search was showing me the wrong information earlier, but this, I did check the documents. The binary compare the two documents was actually the same. So they are the same document. They're just named differently. However, the interesting thing here is we have another 151-0367. Well, there's part of the problem and some of the confusion. The MPSH05 cross-references to the 151-0637. The other part number is 151-0367, not 0637. So transpose the 3 and the 6, and we get a different transistor number. We get the A5T3571, which is a much faster part. It's actually double the speed. So now what we need to check is yeah, it's a so if we look over here, it's 1.2 gigahertz part number. Now we need to check and see what the spec is on the 465 for these transistors. Okay, so we have alleviated a little bit of confusion. 367 is a 1.2 gigahertz transistor. 637 is a 600 megahertz transistor. 650. So let's check the 475 datasheet, or 475 service manual. Well, I'd say this about confirms it right here. Q502, 504, 506, 151-0367 silicon NPN, which actually cross-references to an SKA 6516. See if that'll actually pull anything up. Well, I can pull up no data sheets on the SKA 6516, but I was able to pull up some data sheets on that AT part number. And I can honestly say the transistors match more of that AT part number. So that clears up a little bit of the confusion. It's 0367, not 0673. Or 0367, not 0637. But now the question is, so as a direct replacement, the part number that I did use in the other scope was a bit slow. We have a 200 megahertz scope. That's a 600 megahertz part. Is it suitable? It did, when I did the calibration process and ran through the trigger calibration routine, the scope did trigger like it was supposed to, and it did meet specifications. Okay, so the part that was recommended to me, when I asked the question, I was told these should be replaced on site. Now I'm not 100% sure. When I did replace them in the scope with the recommended part number, which was the KS part number, that would have been a suitable replacement for a MPSH transistor. It's a little slow for a replacement for this specific part. So couple of things for testing. Come back out here. We're going to take a look at and see if, so we answered a big question. Now, I don't know if we can answer the other question of, are these things actually bad or not? So, if I hit go, we show the diode here. Now, somebody, another technician who I was talking to, their testing said if they put their finger on the leads and then ran the test, the diode went away. Mine did not. So, not necessarily a phantom diode. If this part is not supposed to have a snubber diode like that, this would be a faulted out part. Now, the other indication was the corrosion on the leads. This one doesn't have any of the corrosion on the leads. Also, this is a later model serial number board. So this one, which is why I've been using this one as my test subject to figure some of this stuff out. Let's check on a curve tracer. Okay, we have our handy curve tracer set up. I have the test transistor in there, and we're going to be testing at 25 volts. And don't need much wattage for this. We're on 2 microamps base step, 5 volts collector, and a 0.5 milliamp vertical. So we'll give it some go. And we have a nice looking transistor in the beginning. And then, so we'll do, that's 10 volts of collector, 15, 20. Now, if this is the higher frequency part, it should break down right around 25. If it doesn't, it's the lower frequency part. There's the breakdown. You can see it kind of hooks up just a little bit. I'm not hitting it too hard, but if I back it off, you can kind of start to see, and we'll give it a little bit more gas. Different series resistor. There you go. There's the breakdown a little bit better. So you can see it, especially at the top, it's really starting to ramp for current draw. So this is about as hard as I want to push it. But we are hitting the 25 volt collector emitter breakdown as specified by this part. So we have a functioning transistor, but let's look at that diode and see if it'll actually pass some current. For this, we're going to use the DMM 6500 in diode mode. As soon as I find it, there we go. Nope. Diode, there we go. Now, what we're going to do is we are going to do 1 milliamp of test current across the transistor. And I'm going to get some grabber leads because I don't want to do this with probe leads. Okay, so when we're hooked up collector to emitter, proper orientation, we have an overflow and the transistor's off. Now we have no base drive. This is to be expected. If I hook up here and we reverse it, we have a 750 milliamp drop, or millivolt drop at 1 milliamp. Now, given that this was a high frequency component, it was also put out that my Keithley will go up to 12 volts and check when you're doing the diode check. That is true. Now, 12 volts is not going to be able to get over the collector to emitter breakdown voltage of 25. We saw that on the curve tracer. So that's well within the operating range of the transistor. We do know this is a good transistor, as checked on the curve tracer, but it passes current in the reverse direction. So here's the question. Is this expected, or is this a fault? That's where I'm still out. I don't know if this transistor needs to be replaced yet or not. I would not use, I need to source a different part number if I do need to replace this transistor with it being a fault, but I'm not 100% sure at this point. So, given that the DMM was in question, let's move up to the SMU. The reason to test using the SMU is because there was some questions about possibly the high-frequency transistor going into an avalanche state. I have my doubts about that, but we'll hook this up. And what I'm going to do is I'm going to set, I want to measure voltage, I want to source voltage and measure current. So here's what we're going to do. We're going to set a source voltage of 1 volt, and we are going to set a current limit of 1 milliamp. So the SMU is not going to put out any voltage over 1 volt, so we shouldn't have near enough voltage to get the transistor excited into an avalanche state. And we'll go ahead and turn the output on. And when the transistor is reverse bias, we see us hit the current limit of 1 milliamp, and we develop 751 millivolts across the transistor. So, again, we'll do the finger test, and I will put my finger across the collector and emitter of the transistor, and we'll watch this come down, but it's not going to come down as far as you think. And I'm doing this in real time. No cuts, no nothing. And we're getting close to stabilizing right about there. 0747. Are we going to make 4.6? Yeah, we're going to make 4.6. So I'm still holding on. Output's still on. Nothing's changed. And we'll go from there. So, and I take my finger away and it climbs back up. So what is going on with this device? Is this faulty? Is this not faulty? I'm not 100% sure. One of the reasons I'm not 100% sure is at extremely high-speed devices, sometimes they act kind of funny. These are some of the fastest transistors I've had to work on and play with. So, I'm truly not sure. What we'll do is we will source voltage and measure resistance. And we're still at current limit, which is fine, but we have 1.5 volts in climbing. And we have, when the transistor is reverse bias, you can see this as a resistor between the emitter and collector of 750 ohms. Given that this is a 1.2 gigahertz part, is this normal? I don't have a definitive on that one. Now, I'll shut this off. It'll give me an error because it's in high Z, which is fine. We're going to source voltage and measure current again, 1 volt, 1 milliamp. I'm going to flip them around. So now we have the polarity correct. So we have 1 volt, current limit, 1 milliamp. Nothing's making it through that transistor at all. We have no current flow. So there we go. So we're at 1 volt and we have femtoamps of current flow. This is 0.0 nanoamps. So nothing's really moving through this transistor. This could be ambient noise. Again, remember we have open leads and a few other things. This is not the ideal way to measure currents this small. So nothing's making it through the transistor. So now, that poses the question, is this transistor healthy? Is this transistor unhealthy? I don't know. The conclusions the jury is out on this one. Please weigh in on the comments. Let me know what you guys think. Would you change it? Would you not change it? I don't know. Some of these units aren't mine. I do what the customer tells me. But looking for more information on this one. So if anybody has any thoughts, please leave them in the comments below. And we'll take a look at this probably again. Okay, let's see if we can answer, does the scope suffer performance degradation? Keeping in mind that I have not serviced this unit yet at all. I have serviced this unit, and it's good to go. This one's been finished. Now, one thing I did notice is on the 475A, we go down to 5 millivolts per division. On the 475, we actually have a 2 millivolts per division range, so I can go down one more. So I also have more spaces on the time base on the 475 as well. Funny thing is, these are spec'd differently. So the 475 is a 200 megahertz scope, where the 475A is a 250 megahertz scope. So a little bit of weirdness there. Just different things Tech did during the time. So we're looking at trigger performance. I have the trigger set to low frequency rejection, but we'll switch them down to DC. So everything is fair, because we're going to really turn some speeds up. 10x magnifiers on. They are set at 0.01. So we are actually at 0.001. 1 nanosecond per division on each scope. And I'm going to make this fair. We're going to cut some amplitude down, because we have a very low amplitude signal. But we do have the ability to lock in. So let's also interesting, as I sweep the trigger back and forth, comes and goes, whereas this one behaves as you would expect. Bear in mind the transistors have been replaced here, the transistors have not been replaced here. So is this a fact of this diode leakage current that we're thinking about is showing up in here? Don't know at this point. But definitely interesting. It's also not helping this scope that it's open. There's no case on it. So let me get a case on this, because I want to see if it's still doing this in the case. That could be an indication of these transistors are acting funny where the new ones aren't. Now, I poked around online and I looked. I was not able to find any 1.2 gigahertz transistors to replace these with. 650 megahertz is about the fastest I can find in a TO92 package. So that's another wrinkle in this whole situation. But let me get a chassis, or a case, and put this chassis in a case. Alright, as expected, we had noise in the trigger line because of the lab. For those who follow the channel, especially with some of the lower distortion measurements that I have done, you will know that I do not have the quietest lab on the planet. So, we have no ghosting trigger over here. We have no trigger over here. This is a very low amplitude signal. It's 5 millivolts. 10 millivolts, technically. Going into each scope. What I'm going to do is I'm going to wind up the frequency. I'm not going to change anything else. Just going to wind up the frequency. And we're going to see what runs out of gas first. Does the trigger run out of gas, or does the vertical run out of gas? So, at least for this guy, my money's on the vertical, not the trigger. But I'm not sure. So, we'll do 250. Now, as I speed up the frequency, the amplitude is going to decrease just due to the negative bandwidth of the vertical amplifier. Some slight adjustments on the trigger to get a stable trigger would not necessarily be a fail. Not being able to acquire a stable trigger would be a fail. So depending on our trigger point, as the amplitude falls, we may fall out of trigger, in which case I might be able to bring it back. But that's what we're going to test. So we're going to step it up by 50. For this testing, I am using my HP 8657A. Frequency-wise is backed up by the rubidium. And 250 megahertz at 5 millivolts. So we kept trigger here. We lost it here, but let's see if we can bring it back. We can. And I can lock back in. So give me it back. There it goes. Okay. This is going to be pretty fiddly. Let's go to amplitude 3. Oh, nope. Frequency 300 megahertz. And we lost it on both, which is fine. See if we can bring it back. Okay, I can't bring it back. I had to flip over to low frequency reject on the 475. Flip it back up to low frequency reject. And the trigger is starting to fuzz out. So this is about the borderline, the borderline of where the trigger is going to be useful. I'm going to bring it back by stepping up the amplitude to get more signal, because that'll be easier for the scope to trigger on. You're also typically not looking at 5 millivolt signals. So we'll go to amplitude to 25 millivolts. And we will back this. There we go. All right, so we have good amplitude on both sides. This one, dirty cam switch. I have not serviced anything in this scope yet. I've just fixed the power supply. So this would be a factory calibration or whoever the previous owner was. But this one's actually locking in very well. And it's all set. So now that we have more amplitude, let's dial it up a bit. Frequency 350 megahertz. I can get a stable. I'm having a fight with the trigger now. It's really not wanting to trigger. Yeah, there's not much left. So let's take a look at but we're also way down in amplitude too. So let's kick this down, give it some more signal, see if we can't lock into this a little bit better. Because we're not thinking about, or we're not questioning the amplitude accuracy. We're actually questioning the trigger on this one. So we're fighting. So the question is, can we stabilize the trigger with we do have a nice and stable trigger there. So we do have stability of trigger. Let's go to 400. And I think both are flat. No? We're still triggered. But where'd my trace go? I'm almost out of vertical bandwidth at 400 megahertz. Let's see. I'm surprised this has this much amplitude. No, it's resonating. There is no trigger there. Okay, so yeah, 400 megahertz. We run out of gas on the 475. We still have trigger on the 475A. So here's some low frequency signals coming from my signal generator. Everything looks healthy. These look all right. That fuzz and the thickness on the horizontal, I think, may have been part of the trigger, why they use such high frequency transistors in the trigger circuit. We were getting kind of up there. So, should we blanket replace those transistors for the diodes? One, I'm still not sure if that is a, quote, failure mode or if that is a by design aspect. I'm not sure. I'd like to get some clarification on that. Am I going to shotgun replace the transistors in a 475 anymore? Probably not, especially knowing that the frequency disparity between the parts. Good news is we haven't done this too many times. That 475A tube is much healthier than the 475. That is for sure. Like I said, not sure I'm going to shotgun replace these transistors anymore. I don't know. I'd like everybody to weigh in on the comments and go from there. Obviously, if an owner has a scope in the lab, they tell me to replace the transistors, we will. We know we can get spec out of the 650 megahertz transistors. The real answer is the vertical runs out of gas first. All right, I hope that may have cleared up a few things and gotten some more information out there since we were talking about this and doing a bunch of other things. Definitely comment down below what you guys think and let me know. I'm interested to hear everybody's thoughts. As always, I'm in the comments between videos. If you have any questions, comments, or concerns, comment section is where it goes. There's also ways to reach out to me on Patreon and an email link for everyone. As always, I hope this was informative, and I will see everyone in the next video. Bye for now.